Hi, in this video, we want to take a look at generalized least squares. All right, so this is very similar to the least squares that you come across in multiple linear regression, simple linear regression. No, but there's a twist. So this is going to be a generalization of it, just like the name says, generalized least squares. Okay, so remember, our assumptions for regular old vanilla regression is one, we have the model structure. So y is equal to y-intercept plus coefficient times predictor, and add those up. Okay. Second one is that the expected value of the residuals is 0. The third assumption is that the variance of the residuals is constant with respect to x, with respect to our predictor variables. And last but not least is that the covariance given x between any two observations is 0. And that when I say covariance, I mean covariance on the residuals. So covariance on the residuals given the predictor is 0 all the way through. All right, so let's think about those last two. Well, we can represent those last two as just saying that the covariance matrix for our residuals is equal to the identity matrix times a sigma squared scalar value. Okay, so what if that identity matrix part is not correct? So what if I'm in a situation where either, one, we don't have constant variance of the residuals with respect to x, or we do not have covariance 0 between observations, or maybe both. Okay, so we want to deal with this. All right, so how do we adjust this? Well, our model, what we're going to do to just kind of change what our model is that I'm going to say that the covariance is equal to sigma squared times v. All right, so in regular linear regression, this v is the identity matrix, and it's very nice. It's diagonal. It's all ones. I mean, everything is just beautiful about it. Well, here, what we're saying is that v is some known covariance matrix. Okay, and so why do we say that it is known? Well, how many entries are on a covariance matrix? Well, n squared, right? And it's a symmetric matrix. So we've got n down the diagonal and n choose 2 above the diagonal. All right, now if you think about that, n is the number of observations I have. That means I have altogether n times n plus 1 divided by 2 parameters to estimate if the covariance matrix is not constant, is not known. Okay, that's a lot. So for things to work out, we go ahead and just make the assumption that the covariance matrix is a known matrix. All right, so it's covariance matrix, so that means that it's going to be symmetric and it's going to be positive definite. All right, and for everything that we talk about when we talk about generalized least squares, we're going to say that our predictor variable matrix is full rank, and that will, when I say full rank, it's including the constant vector. And all right, so this part is the same. Expected value of the residuals is equal to 0. Expected value of y is x times beta. And here is our linear equation for y. All right, so if we're in this situation, then our coefficient estimate is this formula here. Now, this will look very familiar to you from ordinary least squares regression, that normally I would have x transpose x right here, but there's a v inverse in the middle for generalized least squares. Here, it's x transpose, then normally I would not have the v inverse, it would be y. So x transpose y would be regular ordinary least squares. So this is very similar. It's just that on the right of my x transpose twice, I have v inverse. Now, this is going to be a best linear unbiased estimator of the coefficients. All right, that's nice. And basically to prove that, you do exactly what you do to prove regular ordinary least squares estimates are blue. Okay, well, what about the covariance on the estimate of the coefficients? Well, it's very much the same, except I've got a v inverse between x transpose x. All right, I mean, that feels natural. All right, now what about my estimate of variance? Well, it's very similar. We can notice that I've got y minus x times beta hat transpose. I've got y minus x times beta hat over here. And in the middle, once again, we have V inverse. All right, well, I mean, that should not be shocking at this point. And we'll notice that if I didn't have this V inverse, I would just have sum of squares error up top. It would be my regular S squared estimate. All right, so now I can go through and work through this. If I distribute the transpose and I distribute the V inverse across this, and I distribute and do my matrix algebra work over here, then after I'm done with all that, I factor out the y's. I can see that my variance estimate just works out to be this. All right, so I've got y transpose on the left, y on the right, and I can so this is just a scalar, so I can put that really anywhere I want. And in the middle, the main thing we need to look at about this is that's just a matrix. All right, so that means that we have a quadratic form. Hey, we have theorems from previous chapters about dealing with quadratic forms. Isn't that great? Isn't this exciting? Well, if we work through this, work through the details, we're going to see that this is an unbiased estimator of sigma squared, which is nice. All right, so how do we prove this? Okay, first thing we're going to prove is that this coefficient estimate is blue. So it's the best least variance unbiased, best linear unbiased estimator. All right, so first and foremost, V is positive definite. That means immediately that we know that there's like a square root to V. So we're going to say that that is P, and P times P transpose is equal to V. Okay, so let's go ahead and take this equation. We're saying that this is our model, right? Our model is that y is equal to x times beta plus epsilon. Well, let's go ahead and let's just multiply everything by P inverse. Okay, so multiply everything by P inverse across here. All right, so now let's go ahead and take expected values. If I take expected value on the left, I get the expected value. And then, oh, sorry. And there's a little bit of movement around that. If I consider this, oh, let me back up. I kind of jumped the gun. Let's think about this thing. For us, that's just the y term. The x is a constant, so not going to be a whole lot going on there. But when I take the expected value here, the expected value on this is going to be P inverse times epsilon, which is P inverse times expected value of epsilon, which is P inverse times 0, which is 0. That's going to come up later. All right, so now let's go ahead and take care of the covariance. So in this model format, epsilon is all of the randomness. So in this format, epsilon is the only thing that has a distribution. Everything else is a constant. So as I work through this, I only worry about epsilon in terms of like statistical structure of expected values, variance, stuff like that. All right, so let's take the covariance on this part of the equation. Well, we have a formula for that. When I take the covariance of a matrix times a vector, I take the vector out to the front, take the transpose to the right, and then the covariance of the random part in the middle. All right, well, we know what this is because we made the assumption during the beginning of the theorem. We know that this is sigma squared times V, so boom, we put that in there. Okay, well, now remember that V is the same as P transpose. So I'm going to replace V with P transpose. Now, what am I going to do? Well, I'm going to go ahead and factor out a scalar, because I can factor out scalars in matrix multiplication all I want. And then I'm just going to rearrange the order. So I can see that we're going to have P inverse P, which is going to be the identity matrix, P transpose times P inverse transpose, which will also be the identity matrix. And so we can see that the covariance on P inverse epsilon is equal to sigma squared times I, which in fact is like the regular ordinary least squares covariance assumption, right? All right, so what this shows is if I modify things by, the square root of, not the square root, but the factorization of V, I can actually get back to ordinary least squares. So this means I have a direct connection. So if I know what V is, I can convert my situation to ordinary least squares. All right, well, let's do that. So now, because of this work here, this result with sigma squared times I, that tells me that this equation satisfies regular old ordinary least squares regression. All right, well, if it satisfies ordinary least squares regression, I'm just going to drop that like it's hot straight into the regression equations. Let's do that. All right, so here, my target variable is P inverse Y. My predictor matrix is P inverse X. And my random term is P inverse epsilon. All right, so I'm just going to take them and I'm going to put them in the places of each of the terms in regular ordinary regression. All right, well, remember it's X transpose X, then inverse. So I take this, I put it in there, inverse. And then we have X transpose Y. So here I put P inverse X transpose, and then instead of Y, I have P inverse Y. All right, so we know that this is going to be blue for this P inverse Y model. Okay, so now let's do a little bit of manipulation. I know that this is a transpose. If I apply the transpose to individual terms, that switches the order. All right, so I have X transpose, P inverse T, P inverse, and then X. And then I'm taking this, I'm switching the order, so I get X transpose, P inverse, P inverse, and Y. All right, so this is the same as P transpose inverse. This is the same as P transpose inverse. Well, we said that V is equal to P transpose, right? That's how we got P in the first place. So let's go ahead and replace this business with V. Let's replace this business with V. All right, so now I can see that I end up having X transpose V inverse X inverse X transpose V inverse Y. All right, so now, because this is blue for the P inverse Y model, I know that this is going to be blue on this, like this is going to be blue. It's going to be the best linear unbiased estimator. Boom, we got it. All right, now, part 2 of the theorem. Here, the covariance of our coefficient estimate is very similar to what we have in regular linear regression, except we have a V inverse smack dab in the middle of the inverse part. All right, so let's take a look. How do we do this? If I remember correctly, your textbook didn't do it, but it's just such an easy problem. I couldn't resist doing it. All right, so let's take the covariance of our coefficient estimate. So now we figured out from the previous work, we know what the coefficient estimate is. So what I'm going to do for the coefficient estimate covariance, I just replace it with the matrix formula. All right, now I look at this. Remember, the X's are known constants. The V is a known constant matrix. All right, so when I look at all of this junk, I realize that the only thing that has any randomness is that Y value. Okay, so the only thing that has like a covariance aspect to it is Y. So what I'm going to do, I'm going to apply that matrix formula once again. So all of this junk, the inverse, the X transpose, and the V inverse, this is all just a constant matrix. Since it's a constant matrix, I'm going to use my covariance formula. I'm going to take the constant matrix, put it on the left. I'm going to take the constant matrix and take its transpose, put it on the right. All right, things are looking good. So here, this stays the same. Here, I'm going to take the transpose and I'm going to switch the order on everything. I'm going to apply transpose everything, switch the order. Now, a lot of stuff is symmetric in this. So you're going to see that boom, 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 that transpose aspect after I switch order is going to disappear. All right, so this part stays the same. Now the covariance of Y by assumption is sigma squared V. All right, I'll leave that alone for now. Now here I go through and I'm switching the order and taking the transpose, but almost everything is symmetric, so transpose doesn't do anything. So here, V inverse transpose goes there, X transpose transpose goes there, and then this inverse transpose goes there. All right, so now I look through this. I see that I've got a scalar that I can factor out. All right, I'm going to do that. And I notice that I've got a V and a V inverse here. Huh. You think this is going to cancel? Yes, they are. All right, so these two cancel. This V inverse is left alone. This part I leave alone. This part I leave alone. Okay, so now I've got sigma squared, then the inverse, then the same thing without the inverse, and then the inverse again. Well, these two are going to cancel out because they're inverses of each other. So I'm left with sigma squared, and then this inverse term, boom, we got it. All right, so that's part 2 down. I know this is dense material, but this is exciting stuff. This is good stuff. Last but not least, our S squared formula, which is very similar to our sum of squares error formula, but I've got V inverse in the middle, that this is an unbiased estimator of sigma squared. All right, so how are we going to do this? Well, I'm going to take the formula and I'm going to focus on the numerator. Since it's a fraction, I'm going to focus on the numerator, work all that out, and then deal with the denominator later. Okay, so let's take the numerator like this. Just, take it right off the top. I'm going to distribute the V inverse across this parenthesis. So I get V inverse Y, V inverse X, beta hat. All right, so now I'm going to go through these two parentheses. I'm going to distribute everything. All right, so distribute the Y, get this. Distribute the Y, I get that. Distribute X beta hat to here, I get this. Oh, and there should be a transpose on this bad boy. Should be a transpose. And then I distribute this to here, I get that. Okay, so now think about it for a moment. I've got Y transpose on the right and beta hat, sorry, Y transpose on the left, beta hat on the right. All right, so that is going to be a 1 by n times the matrix, and then it's going to be a k by 1 vector here. So I know that this is actually a 1 by 1. If I apply the same reasoning here, this is also a 1 by 1. If I think about it for a moment, these are the same things in different order, but they end up giving me a 1 by 1. This means that these are actually the same value. So since these give the same value, let's go ahead and put them together. All right, so now I'm looking at this. Let's go ahead and replace beta hat with the formula for beta hat. So I'm going to replace this with its formula right here. I'm going to replace this with its formula right here. Okay, so now this term comes from here. This term goes here. This term on the next line is this long part right there. Okay, so now I look at this and I notice that I've got a bunch of stuff that cancels. These two cancel out, for example, and then something else cancels out after that, I believe. Oh, okay, yeah, so these two cancel out. After these two cancel out, you'll notice that this is the same as the reduced version of this, except for it's got a -2. If it's the same thing, but with a -2, put them together, you get -1, right? Boom, we've got that. Now, I look at this, and I notice I've got Y transpose on the left, Y on the right, Y transpose on the left, Y on the right. I can factor out the Y's. Okay, boom, I've got this. All right, so now I've got my matrix formula. So this is nice because this is what in this format, I have more tools to work with because I've got tools to work with from chapter 2. All right, so now let's go ahead and take the expected value. Realize that this is a quadratic form. Since this is a quadratic form, that is to say it's Y transpose A times Y. So I have Y transpose, constant matrix, Y. I can use theorem 5.2a. All right, 5.2a tells us something involving the trace and expected value transpose A expected value. All right, so this theorem, when I apply it to this formula, it's going to be in this format, but I have to go through and replace the A's. All right, well, I know that the covariance of Y is sigma squared times V. So for the moment, I'm not changing what A is, just because there's a lot going on here. And then I've got beta transpose, X transpose for the expected value of Y. I have X times beta for the expected value. All right, so now here, I've got the trace of A times V. Now this, what I'm going to do, I'm going to replace A with all of the stuff in the middle here. And there's a lot. So I go ahead and just slap it in there. Now, I'm going to do something very similar to this. All right, so on this step, I have A times V. I know that if I take A, which is what's inside here, if I multiply V on the right here, that's going to be I. If I multiply by V on the right here, then the V inverse and the V are going to cancel out. And I get all of this business here. And it's all inside the trace. Now, let's see what happens with this. Oh, so I'm going to go ahead, I'm going to distribute the beta transpose, X transpose. I'm going to distribute X times beta. Sun is in my face. All right, so now I've got, so here is the trace term. All right, so remember the trace is the addition of the diagonal. So I know that I can break that up into addends, the trace of addends. So I can replace this I can pull out the I and replace it with the trace of I. So that's going to be just an N. And here I still have the trace of what's right there. Now here, I look through and I notice that this cancels with that. Since this cancels with that, I'm going to have some stuff disappearing. I get beta transpose X transpose V inverse X beta. And I notice that that's the same thing as what I have right here. So then that just cancels out to be 0. Beautiful, beautiful. All right, so now things are looking a lot cleaner. I look at this and I go, hey, with a trace, I can change the order of my matrices freely as long as multiplication is defined. Okay, well, I see that I have X transpose V inverse X inverse, and I've got an X transpose V inverse X over here. So if I take this X transpose and using the commutative property for the trace, move it here, I have this item times its inverse. Boom, I've got that. So that means it's going to be the identity matrix. Now, there's a catch on this. There's something we have to watch out on this particular step right here. All right, so here, this is the trace, and what's the number of rows, what's the number of columns on this? When I got this one, well, this was an n by n matrix. Well, why is that? Because I took A and multiplied by V. All right, so how many rows and columns does V have? V has n rows and n columns. All right, so that's why this is an n by n identity matrix. Down here, this is coming from X transpose, right? X transpose, how many rows does X transpose have? Well, how many columns does X have? X has n plus 1 columns, so this is a k plus 1 by k plus 1 identity matrix. So the trace is k plus 1. Boom, I've got this. All right, so now with the fraction, when I divide by the numerator, I can see that I'll have an unbiased estimate. All right, now, since V is positive definite and X is full rank, we know that X transpose V inverse X is also positive definite. All right, now, here's our what we call the generalized least squares estimate. So here, it's very much the same as our regular formula, except I've got a V inverse on the right of X transpose. I have a V inverse on the right of X transpose. Now, standard least squares just uses V equal to I. So if I'm working in generalized least squares, I have the option at any time to go back to regular least squares just by changing my covariance matrix. All right, now, if Y is a normal length n vector with expected value X beta and covariance matrix sigma squared times V, X is full rank, V is known, positive definite, x is n times n plus 1, and n is strictly less than k plus 1, then the maximum likelihood estimate of beta and sigma squared are exactly what we want them to be. Well, except for, since it's MLE, we don't have the k plus 1 part on the bottom. So this is a biased estimate, but it's very, you can see that it's very similar to the maximum likelihood estimate of least squares regression. All right, so the only difference is that I've got this V inverse stuff like in the middle in a few spots. All right, how do we prove this? Well, it's very much like the maximum likelihood estimate for regular least squares. What I'm going to do, I take the density function and I just, I treat beta and sigma squared as variables and I plug it in. And now, when I look at this, I know that the determinant of sigma squared V is going to be equal to sigma squared to the power of n times the determinant of V. That's a property of determinants. So I replace that here. And so this is inverse. So I know that the sigma squared pulls down to the bottom of the fraction. All right, so now I'm going to take natural log of both sides of the equation just to make this easier. So remember that in this situation, if I want to maximize or minimize, I'm going to be doing calculus. I'm going to be taking, differential calculus. All right, so I'm going to be taking a derivative. I want this to be the easiest derivative humanly possible. So I'm going to take natural log of both sides. Remember, if I optimize on natural log, I optimize on the regular function on the inside of natural log because it's a strictly increasing function. Okay, so now I take natural log of this entire thing. Now at this step, I take the partial derivative with respect to beta, take the partial derivative with respect to sigma squared, set them equal to 0, come up with a justification for why it is a maximum, and then boom, we are done with it. So I'm not going to go through the calculus that's left as a homework problem. I didn't want to do it just because I felt lazy when I was writing up the notes. It's not hard. I mean, if you're unsure of what to do, go back to my video on the maximum likelihood estimate of least squares regression and literally just follow the same steps. It works out exactly the same. All right, so now let's do an example. Let's consider the situation where we have constant variance and we have constant covariance, but that constant is not 0. So ordinary least squares would have constant covariance of 0. We're saying we have constant covariance of something else, and we're going to call that rho. All right, so our covariance matrix is going to be sigma squared on the diagonal, and off the diagonal, it's going to be sigma squared times rho. All right, so sigma is equal to sigma squared times 1 minus p times I plus p times the 1 matrix, and that is sigma squared times v. And here we can represent it in this manner. And just to make it a little bit easier to work through, we're going to go ahead and use a centered model. So we're going to say that y is equal to j centered x times alpha beta 1 plus epsilon. So this is just the same betas that we would get in ordinary least squares. All right, well, if I apply the estimate, I just used what we worked out a moment ago, we get this. Okay, so I'm going to set x to j and then centered x. And the reason why I'm setting x equal to this is just to make life a little bit easier. And so when I do that, x transpose x, v inverse x is equal to this bad boy right here. Here's x transpose, here's x and the v inverse. All right, and I know that this is a partition matrix. Let's go ahead and apply our partition matrix formula. And we get this 2 by 2 partition matrix also. Well, remember that v is 1 minus p times I plus p times j. So if we use the inverse formula for this type of problem, I know this is a times I minus bp times j, where a is 1 over p and b is 1 over 1 plus n minus 1p. Okay. So now I'm going to plug in v inverse into this formula. So I'm plugging it in up here. And I'm working it out. I can see that I get b times n, where this is b. I get the 0 vector transpose. I get 0 vector. And then I get a centered X transpose centered X. Okay, well, when I multiply by Y, I can see that, so remember that, when I deal with X, X has a constant, a vector on there, and the first vector is constant. That's where the Y bar part is coming from. And so when I do this multiplication, I see I get B times N Y bar, A times centered X transpose Y. Okay. And so we can see that our estimate of beta hat is the sample mean of Y, which should not be surprising. We know that should be true. But then we get X transpose of the centered version, X, and then centered version X inverse, then transpose of centered X, Y. All right, so the maximum likelihood estimate is the same as the least squares estimate. It follows that when we have constant variance and constant covariance, the estimate is blue also, best linear unbiased estimate. So nice. So the punchline is when I have constant variance and constant covariance, regardless of what that constant is, we get a best linear unbiased estimate either way. But realize if I don't do generalized least squares, if I just try to use regular least squares and I'm in this situation, my variance will always be bigger. And so that's bad, even though it will be unbiased. All right, so now we want to think about what happens when we misspecify the error structure. All right, so let's say Y is equal to X beta plus epsilon. Covariance of Y is our generalized least squares assumption of sigma squared times V, but we make a mistake. We don't recognize that we're in a generalized least squares situation. We assume we're in regular ordinary least squares land. All right, so I go through and I use this as my covariance matrix instead of what I should use. Well, what is going to happen? Well, I'm going to say that B hat star is basically the bad estimate of the coefficients. It's not a horrible estimate, but it is less than optimal. I'm going to let beta hat be the optimal estimate. All right, so what am I going to do? Let's take the expected value of beta hat star. All right, well, the x's are constants, so this is the constants times the expected value of y, which is x times beta. So that doesn't change. And I can see that all of this cancels out and I get beta. So either way, if either version of the coefficient estimate is used, I get an unbiased estimate. That's nice. That should be reassuring. That way, if we make a mistake on the covariance structure between our residuals, it's not the end of the world. All right, now let's think about covariance. All right, well, covariance, it's just going to run like everything else, that I have a constant matrix times y. So I use my covariance formula, constant matrix on the right, transpose of the constant matrix on the other side, and then covariance of the variable in the middle. And I know that that is sigma squared times v. Okay, so what's going to end up happening is that all of this junk is going to give me a larger variance than if I would have used the better one. So when it comes to hypothesis testing, I might be getting rid of coefficients that I shouldn't be. So that should warn us. That should give you a heads up to the pitfalls of not having a good covariance assumption. All right, so now let's look at the situation where we have zero covariance, but residual variance is proportional to the predictor in simple linear regression. Okay, so in this situation, I'm going to have a sigma squared as a constant, and then I've got really my predictor variable values in simple linear regression. All right, so what I'm saying here is as x increases, the variance on the residuals increases proportionately, and that proportionality is constant for all of the observations. and I'm on a diagonal matrix, so I have 0 above and below the diagonal, that corresponds to a covariance of 0 between all observations that are distinct. All right, so this is an example of a weighted least squares model. So the correct way to proceed with this is to do a weighted least squares. All right, well, how should I approach this? So X stays the same, but my covariance matrix V, the inverse is just 1 over the observations. So we're assuming that, oh, by the way, I don't think I wrote it down, but all the X's have to be positive for this to make sense. If it doesn't make, what we could do is just take absolute value if we want to make it a little bit juicier, make it a little bit more interesting. Okay, well, I can start plugging and chugging and just start working this out. And this is just basically just crunching out the equations, working through it. And we'll end up getting the covariance on our estimate. All right, what will ultimately happen if we mistakenly use ordinary least squares? The variance will be larger than what the variance would be if we had the correct model structure. All right, so the expected value will be good, but we will be, the variance will be larger, and we'll be prone to thinking that a slope is 0 when it's not. All right, well, that's all I've got for you. Take care and goodbye.